Assalamu alaikum dear student. Bismillahir Rahmanir Rahim. Today we will start our lecture from group 4 elements. Physical properties of the elements. Melting points and boiling points. As we move down the group from carbon to lead, the melting point as well as boiling point generally decreases, although the decrease is not in a regular order. This decrease in melting point as well as in boiling point indicates that interatomic forces also decreases in the same direction. The melting and boiling point of carbon and silicon are notably high because of the tendencies of these elements to form joint molecules. The low value for tin's melting point compared with lead is presumably due to forming a distorted 12 coordinated structure rather than a pure one. Brittleness. Carbon as a diamond is of course very hot, reflecting the strength of the covalent bond. However, if you hit it with a hammer, it shatters. Silicon, germanium and graphene are also brittle solids. However, white tin and lead have metallic structures. The atoms can roll over each other without any permanent disruption of the metallic bonds, leading to typical metallic properties like being malleable and ductile. Lead in particular is a fairly soft metal. Here you can see in this graph that melting and boiling point of group 4 element decrease down the group. Electrical conductivity. Carbon as diamond does not conduct electricity. In diamond, the electrons are all tightly bound and not free to move. Unlike diamond, silicon, germanium, and graphene are semiconductors. White tin and lead are normal metallic conductors of electricity. Therefore, a clear trend from the typically non-metallic conductivity behavior of carbon as diamond and the typical metallic behavior of white tin and lead. Electronegativity. Carbon is the most electronegative element of this subgroup and the electronegativity decreases with the rise of atomic number but not a regular manner. This is probably due to the filling of the d orbital in case of germanium and tin and f orbital in case of lead. Ionization energies. The ionization energy values decrease on moving down the group from carbon to lead, although the decrease does not occur in a regular order. The irregularity in the decrease of this value is due to the filling of intervening d orbital in case of germanium and tin and f orbital in case of lead, which are not able to screen the valence electrons effectively in elements following them. The turns from non-metal to metal in the group 4 elements. Structure and physical properties. First of all, structure of the elements. The turn from non-metal to metal as you go down the group is clearly seen in the structure of the element themselves. Carbon at top of the group has joint covalent structure in its two most familiar electrodes, diamond and graphite. Here is the picture of diamond, a small pod of three-dimensional structure of carbon atoms, each joined covalently to four other atoms. Diamond has a three-dimensional structure of carbon atoms, each joined covalently to four other atoms. Exactly the same structure is found in silicon and germanium and is and in one of the allotropes of tin or alpha tin. The common allotropes of tin is metallic and has its atoms held together by metallic bonds. The structure is a distorted close-pack arrangement. In close packing, each atom is surrounded by 12 near neighbors. There is therefore a clear trend from the typical covalency found in nonmetals to the metallic bonding in metals, with the changeover obvious in the two entirely different structures found in tin. Oxidation state. This topic explores the oxidation states shown by the group 4 elements carbon, silicon, germanium, tin and lead. It looks at the increasing tendency of the elements to form compounds in which their oxidation states are +2, particularly with reference to tin and lead. Enol pair effect and positive oxidation states. Carbon and silicon show +4 oxidation state, while occurrence of +2 and +4 oxidation states in case of germanium, tin and lead is explained as follows. When two Np electrons form the Ns2p2 configuration are lost, we get the elements in +2 oxidation state. Ns2 electrons inert and hence are not lost in the formation of M2 plus cation. This pair of Ns2 electron is called inner pair of electrons. Since in the group the stability of +2 oxidation state also increased from germanium ion to lead ion. When all the four Ns2p2 electrons are lost, we get the elements in +4 oxidation state, i.e. M4 plus cations are formed. On descending, the group stability of +4 oxidation state decreases, i.e. the stability of M4 plus cation decreases from G germanium 4 to lead 4. Compounds of germanium 2 are less stable than those of germanium 4 and hence the compound of germanium 2 are readily oxidized into those of germanium 4. In other words, compounds of germanium 2 act as strong reducing agent while those of germanium 4 act as oxidizing agent. Here on similar grounds, it can be shown that compounds of tin 2 plus are less stable than those of tin 4 plus oxidation state. In other words, compound of tin 2 plus acting as strong reducing agent while those of tin 4 plus act as oxidizing agents. When we compare the stability of the compounds of lead 2 plus and lead 4 plus ion, we find that lead 2 plus compounds are more stable than those of lead 4 plus, and hence the compounds of Pb4 plus ion are readily changed into those of Pb2 plus. In other words, compound of Pb4 act as strong oxidizing agent while those of Pb2 act as 2 plus act as reducing agent. Here you can see in this equation. Thus, when we compare the stability of metal 2 plus and metal 4 plus cation of germanium, tin and lead, we find that their stability is in the order germanium first, germanium 2 plus, germanium less stronger, germanium 4 is more stronger than germanium 2, tin 2 plus is less stronger, Sn4 is more stronger, lead 2 plus stronger than lead 4 plus ion. Negative oxidation state. Since the electronegativities of the elements are low, they do not have much tendency to form the negative ion. However, carbon forms C4 negative and C2 two negative ions in certain compounds, e.g. Be4 2 plus C24 minus or Be2C aluminium Al4 3 plus C34 minus and Na plus 1 CH3 minus 1. Here these elements have negative charges. The inner pair effect in the formation of ionic bond. If the elements in group 4 form 2 plus ion, they will lose the p electron, leaving the s2 pair unused. For example, to form a lead-2 ion, lead will lose the 2,6p electron, but the 6s electron will left unchanged and inert pair. You would normally expect ionization energies to fall as you go down a group as the electron get further from the nucleus. That does not quite happen in group 4. The first chart shows how the total ionization energy needed to form the 2 plus ion varies as you go down the group. The values are all in kilojoule per mole. Notice the slight increase between tin and lead. This means that it is slightly more difficult to remove the p electron from lead than from tin. However, if you look at the pattern for the loss of all 4 electrons, the discrepancy between tin and lead is much more marked. The relatively large increase between tin and lead must be because the 6s2 pair is significantly more difficult to remove in lead than the corresponding 5s2 pair in. The reason for all these lie in the theory of relativity. With the heavier element like lead, there is what is known as a relativistic contraction of the orbitals. You tend to draw the electrons closer to the nucleus than you would expect. Because they are closer to the nucleus, they are more difficult to remove. The heavier the element, the greater this effect. This affects S electron much more than P electron. In the case of lead, the relativistic contraction makes it energetically more difficult to remove the 6s electrons than you might expect. The energy releasing terms when ions are formed obviously are not enough to compensate for this extra energy. That means that it does not make energetic sense for lead to form 4 plus ion. The inner pair effect in the formation of covalent bonds. You need to think about why carbon normally form 4 covalent bonds rather than 2. Using the electrons in boxes notation, the total electronic structure of carbon look like this. Here you can. On excitations of these 2s electrons, carbon has now 4 unpaired electrons. There are only 2 unpaired electrons before carbon form bonds, though it normally promotes one of these electrons to the empty p orbital. There leave 4 unpaired electrons which can go on to form 4 covalent bonds. It's worth supplying the energy to promote the s electron because the carbon can then form twice as many covalent bonds. Each covalent bond that form release energy, and this is more than enough to supply the energy needed for the promotion. One possible explanation for the reluctance of lead to do the same thing lies in falling bond energies as you go down the group. Bond energies tend to fall as atoms get bigger and the bonding pair is further from the two nuclei and better screened from them. For example, the energy released when two extra PBX bonds are formed may no longer be enough to compensate for the extra energy needed to promote a 6s electron into the empty 6p orbital. This would be made worse, of course, if the energy gap between the 6s and 6p orbital was increased by the relativistic contraction of the 6s electron.